Hi everyone. Today we're going to look at a very special differential equation called exponential growth and decay. And before we begin, we should start with a definition. A direct proportion is the relationship between two variables when their ratio is equal to a constant value. So when we say a quantity y is directly proportional to a quantity x, means that this equation can be written y equals k times x, where k is the constant of proportionality. Okay, so we begin with this AP problem. A quantity is said to have exponential growth or decay model if at each instant in time its, okay, now this is important, its rate of increase or decrease is directly proportional to the amount of the quantity present. And let's just represent this symbolically. Okay, so let y equal the number present at time t. And let k equal the constant of proportionality. So we could represent this definition as follows. So a quantity is said to have exponential growth or decay model. So this is the quantity here. If at each instant in time, its rate of increase-decrease, so that would involve the rate would remind us of the derivative of y with respect to time. So its rate of increase-decrease at each instant, that's dy dt, that's the quantity, is directly proportional, that's where k times comes in, to the amount of the quantity present, which is just y. So this equation is a differential equation, but a very special differential equation, where the derivative is directly proportional to the amount present. And the k is the constant of proportionality, and this is called an exponential growth decay model. When k is greater than 0, we have the growth in the population, and when k is less than 0, we have decay in the population. And many of you may have studied this already in your science class. But this particular equation, differential equation, has a very unique solution. So let's solve that on the next page. Now, to represent the solution to this differential equation, very special differential equation, we will proceed by separating the variables like we always do. So we cross multiply, bring the y over, leave the constant where it falls, so we divide each side by y. So we have dy over y equals k dt. Now we integrate each side with respect to that variable. And on the left side, we get ln of absolute y equals kt, because the integral of a constant with respect to t would be that constant times t. And we always put the plus c we agreed on the x or t side. Okay. Now, in order to solve for c, that at time 0, the quantity is 1,000 bacteria. Let's think of it as 1,000 bacteria at t equals 0 minutes. So when we substitute this in here, we get ln of 1,000 equals k times 0 plus c. So c is simply ln of 1,000. So when we substitute this back into our antiderivative with the correct value of c, we get ln of absolute y equals kt plus 1,000. Now, to solve for y, well, to clear ln, we raise each side to a base of e. Okay, so we put base e on each side. Let me just go back to my black marker. And the e and ln, when they're composed, cancel. So we get e to the kt. Oh, I'm sorry, I misprinted something here. Let me just erase this. Okay, that should have been ln plus ln of 1,000. And then I forgot to put it over here. ln of 1,000. Okay, so now we could split this up into the product of two e's, and because there's a natural log in the exponent, we'll put that here. And when we add the exponents, we multiply by the same base, so we'll write this, e to the kt times e to the ln of 1,000. This gives us 1,000, and this gives us e to the kt. And we only split up the right side when we have e to the sum, an exponent that has a sum of two expressions, one of which is ln. That's when we split up the expression into the product of two e's. So to clear the absolute value, we introduce positive or negative, and we'll move the 1,000 in the front. And we see that there are two possible differential equations, y equals 1,000 e to the kt, or y equals negative 1,000 e to the kt. But the one that satisfies the condition that when t equals 0, y is 1,000 is obviously the first one. So we can generalize the solution. We could evaluate the solution by separating the variables, but it's really worth memorizing the solution for this special differential equation. So the shortcut is this. When we have the differential equation dy dt equals ky, and it must be of this form, then the solution is y equals, now if we go back to what we've circled here, the 1,000 was the amount, the quantity present at time 0. We call this the initial quantity, and I'll rewrite that as y sub 0. E to the kt. To solve for the variable k, we need another point on the function. So I'll say that where y sub 0 represents the initial quantity at time 0. Okay, so rather than redoing this over and over again, from now on, when we have this particular differential equation, but it has to be that form, we could just immediately write y equals the amount present at time 0 times e to the kt. All right, let's take a look at a few multiple choice questions that appeared on this topic. And there should be information to help us solve for C. Well, let's say, here I compiled a sheet of 3 multiple choice questions on this topic. Some of these are involved and some of these are really straightforward. Let's take a look at number 1. If dy dt equals ky and k is a non-zero constant, then what could y be? Well, we have to remember that the solution is in terms of y equals y sub 0 e to the kt. So the solution that's closest to that would be choice 2. I mean, that didn't even need any work. We just have to see which one would fit that form. Okay, let's look at the second one. The weight of a population of yeast is given by the differential function y, where y of t is measured in grams and t is measured in days. So let's just write this down. So y is population of yeast in grams, and t represents the number of days. All right, now this is the key. It says the weight of the yeast population increases according to this differential equation, where k is a constant. So immediately we could write down the solution, y equals y sub 0 e to the kt. At time 0, the weight of the yeast population is 120 grams. So So at time, when the time is 0, y is 120 grams. So immediately, where can we substitute the 120? Into y sub 0. So now my equation becomes this. Okay, so the weight of the yeast population is 120 grams and is increasing at the rate of 24 grams per day. Okay, so this is interesting. We know that dy dt is equal to 24 grams per day. So there's a little twist to this particular problem. So what we'll do is we're going to differentiate this equation. Dy dt equals 120 e to the kt times k by the chain rule. Okay, now dy dt is given to be 24 grams per day at the time 0, because it did say two things are happening at time 0. So we have 120 e to the k times 0, which is 0, times k. So if we divide each side by 120, and this is equal to 120 because e to the 0 is 1, we get k is 1/5. So our equation becomes y equals 120 e to the 1/5 times t. And that's the solution we're looking for. And I believe it is choice B. Okay, let's take a look at the next question. The population P of a city grows according to the differential equation dp dt equals kp. So immediately when we write that, we know that the solution is P equals P sub 0 e to the kt, where P sub 0 is the amount of the population present when t equals 0. Okay, now it says that if the population of the city doubles every 12 years, so when t equals 12, then p is equal to twice this amount, which is 2p sub 0. So let's substitute that into our differential equation, even though we don't know what p sub 0 is. So we could say that when t equals 12, the population, which is 2p sub 0, equals p sub 0 e to the 12k, where t is 12 years. Now we could divide each side by p sub 0. We get 2 equals e to the 12k. We could take the natural log of 2 on each side. And we get the natural log of 2 is equal to 12k. And k is equal to the natural log of 2 over 12. Whichever way we do it, we have to use the calculator to approximate it. So we have a choice. We could put this into our calculator, or we could put this equation and have the calculator solve it. Either way, we should get the same value for k. And when we substitute it into the calculator, we get that k is about 0.0577. So remember, 3 places after the decimal point. And we see that the closest answer to that would be A. And that takes care of some of the multiple choice. Let's take a look at a problem that was in the long answer back in 1993. All right. Now this problem is known as the wolf problem, and it goes like this. Let P of t equal the population of wolves at time t years, where t is greater than or equal to 0. The population P of t is increasing at a rate directly proportional to this 800 minus P of t, where the constant of proportionality is k. All right, so this is like an exponential growth or decay model, but it really doesn't fit the form, because in 1993, students were expected to know how to write an equation when they're given the words that the population is increasing at a rate directly proportional to 800 minus P of t. So if we write that and translate it, we get this. The population P of t is increasing at a rate, so that's its derivative, dp dt. And we're not going to put dp of t. We'll just call P of t p, and we'll just to make it simpler for ourselves. So the population is increasing at a rate directly proportional, so that's equals k, to this quantity, 800 minus p. Now, this does not fit the form that we did before. Our form would have been this. dp dt equals kp. But because there's an 800 minus p, we cannot generalize the solution to the differential equation, so we have to use separation of variables to solve it, whatever they ask for. So in part A, they say that if P of 0 equals 500, which means that at t equals 0, P is 500, find P in terms of K. So let's just solve this differential equation. So we cross multiply, separate the variables. We get dp equals k times 800 minus p times dt. Divide each side by 800 minus p to get the p over to the dp side. Leave the k where it falls. dp over 800 minus p equals k dt. We integrate each side. And we agreed that this side would be kt plus c, but this side would require u substitution. And because the exponent in the denominator is 1, we know that this is an ln integral. So it's ln of the absolute value of 800 minus p, where u is 800 minus p. But we said that the shortcut was to take the coefficient of the p and multiply by its reciprocal. So the reciprocal of -1 is -1. A lot of students missed that when they took this AP. Okay, and that shortcut could only be done when u is linear. All right, now we're going to solve for the c. So we solve for the c by substituting p of 0 is 500. So when t is 0, p is 500. So I get negative ln of 300 equals c. So that's my constant. So now we have to proceed and isolate p from this equation. So let's go on to the next page and do that. So we have this solution, -1 times the natural log of the absolute value of 800 minus p equals kt minus ln of 300. So we have to solve for, we already solved for c. Now we're going to solve for p. And to solve for p, we have to get this ln by itself. So to get ln by itself, we multiply everything by -1. So we get ln of the absolute value of 800 minus p equals ln of 300 minus kt, if we negate it. Now that ln is by itself, we could take a base e on each side, because e is a one-to-one function, and we can do that. And this side gives us the absolute value Now, in the last question, we're asked to find the limit as t increases without bound of p of t. So recall that the function was 800 minus 300 e to the negative k, so this is negative ln of 3 over 2 t. Okay, now to find the limit of that function, we have to review what happens to an exponential function when the exponent is negative. So if you recall, here, when we have y equals 2 to the x, this is what it would look like when we have a positive coefficient for the exponent. But y equals 2 to the negative x would be a reflection of that over the y-axis. So this would be true for this crazy function e to the negative ln of 3 over 2 times t. The coefficient of the t, which is like our x, is negative. And as t increases without bound, our function would approach 0. So the answer here would be that this limit would be 800 minus 300 e to the negative ln of 3 over 2 t. And this piece, this whole piece, even if we multiply the exponential function by 300, approaches 0. So the limit of a constant is just the constant, and this is the answer to our AP problem. So in 1993, what the problem was with this question was that a lot of students didn't know the meaning about the population increasing at a rate directly proportional to 800 minus p. And if they couldn't write the differential equation, they lost total credit on the AP. Please keep in mind that in such a problem with direct proportionality, we have to have the initial condition, p of 0 equals 800, to express the function, to express p in terms of k and t. And then we needed another point on p of 2 equals 700, to find the value of k. So these differential equations are a little bit more involved. Okay, so I hope this clears up the unit on differential equations. I wish you a very happy day and stay well, everyone. Bye-bye.